Hello everyone and welcome to this presentation. My name is Hadi Amirpour from University of Klagenfurt and I will be presenting our paper SLFC or Scalable Light Field Coding co-authored by Christian Timmerer and Mohammad. First of all, I will give a brief introduction about light field imaging and then I will talk about light field compression methods and their challenges. I will introduce our proposed method SLFC, followed by its experimental results, and finally, I will conclude this presentation. Let's see how light field photography works. Conventional cameras usually capture a two-dimensional sample of a three-dimensional world by recording two-dimensional light intensity on an imaging sensor. But light field cameras capture a four-dimensional light field. They not only record intensity of light in a scene, but also they record direction that light rays are traveling in a space. For example, for this spatial point, there are some light rays that are traveling in different directions. In conventional cameras, all of these light rays are integrated into one pixel. But in light field cameras, by embedding a macro lens array between main lens and imaging sensor, we will be able to record all of these rays that are traveling in different directions. Consequently, we will be able to record multiple views of a scene, and finally, we will have a four-dimensional function for a light field. In another way, we are able to record this angular information using a camera array. As you can see here, each of these cameras in this camera array are responsible to capture a different field of view for the same scene. By processing all these multiple views, we are able to generate a light field volume, and this light field volume will enable some post-processing tasks like refocusing, changing viewport, depth estimation, 3D modeling, and synthesizing new views. This example shows how a user can change depth of field for one light field image, or change viewport for the same light field image. Huge amount of data that is needed for a light field image makes compression necessary to facilitate storage and transmission. Conventional light field image compression methods usually convert these multiple views into a pseudo video, as you can see in this example. Then this pseudo video used as an input for a video encoder, and generated bit stream is stored or transmitted. Then a video decoder is used to decode this bit stream and generate our multiple view of a light field image. When we encode this pseudo video using a video encoder, for intercoding, we make these views dependent to each other. Therefore, there will be some challenges that are introduced in compression of light field images. In light field compression, beside encoding efficiency, other features like viewport scalability, quality scalability, random access to different viewports, and uniform quality distribution are among important features and challenges that should be addressed when we are encoding one light field image. In order to increase compatibility with display, capturing device, network condition, processing power, and storage capacity, it's important for a light field compression method to provide viewport scalability. Let's assume that our display is a conventional display. Then we might need to transmit and display only the most central view. But because of dependency that there exists among different views, when we are encoding a pseudo video, we might need to transmit some additional viewports that we are not going to display. In this case, we may waste some bandwidth, processing power, and storage capacity. Similar to viewport scalability, in order to increase compatibility with network condition, processing power, and storage capacity, it's important to provide quality scalability. When a user navigates between different views, it's undesirable to face different quality levels. Here is one example. As you can see here, it's also very challenging to assess quality of this light field because one light field is not only one image, it is multiple views. So when we have fluctuation in quality levels, it would be very challenging to evaluate quality of encoded bit history. Considering all of these challenges and features that should be addressed while encoding a light field image, we introduce SLFC or Scalable Light Field Coding. In SLFC, light field image views are divided into different 7 layers. Let's assume that each of these squares is representing one view. So in this example, we will have 9 by 9 or 81 views that are divided into 7 layers. In each layer, red view belongs to that layer, gray views belong to the previous layers, and black views belong to the next layers. For example, here in layer 2, the central view, which is represented by gray, belong to the previous layer or layer 1. Corner views that are represented by red belong to layer 2 or current layer, and all other black views belong to the next layers. In layer 1, we will have only the most central view. In layer 2, corner views are added, and for the other layers, horizontal and vertical intermediate views are added. For example, in layer 3, we can see that for the top left and top right, their intermediate view, that is the top view, is added to layer 3. So this procedure continues to other layers. For encoding, the most central view in layer 1 is always intra-coded and can be accessed independently. Corner views that are added in layer 2 are encoded independent of each other, but all of them use the most central view of layer 1 as a reference image. What we see encoding of remaining views in the remaining layers as a view or frame interpolation problem. We use deep neural networks for interpolation and improving encoding efficiency. For example, when we want to encode the most right view in layer 3, we will use top right and bottom right views as input for deep neural network. And this deep neural network will synthesize the target view or the most right view. When we look at residual of these views, bottom right, top right, and synthesized view with target view, we can see that synthesized view has much less entropy information. Therefore, it would be much easier to encode the most right view using the synthesized view as a reference frame. For interpolation, we can use many video interpolation methods introduced in literature review, and we selected SEPCONV, video frame interpolation via adaptive separable convolution. In the previous example, if I1 and I2 are top right and bottom right views, then output of SEPCONV will be the most right view and will be the synthesized view. Therefore, for intermediate views in layer 3 to 7, 2 views from the previously encoded layers are used to synthesize these intermediate views. When this intermediate view is synthesized, it is added as a virtual reference frame to the reference list in video encoder. Therefore, to encode each intermediate view, 4 references are used for intercoding. Always the most central view for all of the views, 2 views that are used for interpolation, and the synthesized view. For the previous example, for the most right views, reference views will be the most central view. Top right and bottom right views that are used for interpolation, and synthesized view. Here we compare encoding efficiency of SLFC with some state-of-the-art methods. We use Anchor of JPEG Plano, WASP, Mule, and PSP for comparison. And we can see, for example, for table light field image that SLFC outperforms all of state-of-the-art methods in terms of encoding efficiency. Considering PSP as the best competitor for all light field images, bitrate reduction of SLFC compared to PSP is given in this table, and you can see that up to 45% SLFC can gain bitrate reduction compared to PSP. In terms of viewport scalability, the number of views in each layer is given in this table, and allocated bitrate to each layer at BPP equal to 0.75 is shown in right figure. For example, when we want to transmit only 0.3 BPP, then we can transmit only layers 1 to 4, and we can skip layers 5, 6, and 7. So we are much more flexible when we make all the views dependent to each other. For quality scalability, SLFC provides two quality levels. It's very similar to scalable video coding that is provided, for example, in SVC or SHVC. For quality 1, when we have the most central view in layer 1 and corner views in layer 2, we can synthesize all other views using our deep neural network. So the generated bit stream is considered as a base layer here. But when we use reference views for intercoding of intermediate views in layers 3 to 7, then this additional layer can be used as enhancement layer and improve the quality of intermediate views, and it is considered at quality level 2. For random access, we use a metric from JPEG Plano. Random access penalty is defined as total amount of encoded bits required to access a view divided by total amount of encoded bits to decode the full light field. Here you can see, for example, for Greek light field image at BPP equal to 0.75, that for accessing to most central view, we might need only 4% of whole light field, or for corner views, we need only 6% of whole light field views, and in the worst case, we will need 24% of whole light field. Some methods in literature review try to allocate higher bit rates to reference views in order to increase encoding efficiency. However, we can see that there is a high fluctuation in quality of different views. But SLFC provides very uniform quality distribution among all the views in a light field encoded in a specific bit rate. For example, we can see here PSNR heat map plots for Greek light field image that quality of all the views are very similar together, and they are around 36 dB for all the views. Here is conclusion of our presentation. SLFC utilizes a deep neural network to synthesize intermediate views. These synthesized views are used as visual references for intercoding, and consequently it will increase and improve encoding efficiency. And in this way, SLFC provides high encoding efficiency, viewport scalability, quality scalability, random access, and uniform quality distribution. And finally, I would like to thank you for watching this presentation.